Hello everyone, I'm Megha Daga. I'm part of IoT division in Qualcomm. I lead the AI charter for the product management across the IoT portfolio. And today I'm glad to be speaking about how we are enabling vision AI applications at the edge for industrial inspection applications. So with that, we will get going. Just as a beginning, IoT itself. So there are different sides of IoT, phases of IoT, from consumer IoT to enterprise IoT, and all of that going together into edge networking IoT. We have been heavily focusing on all those three areas, and we can see that the demand for digitization across all these three different segments have been exponentially growing. There have been various different drivers which have been enabling and asking for those digital transformation. Some of them listed over here with respect to connectivity, more and more compute performance, still at a low power because this is all at edge, and at the same time, more and more intelligence coming into this space. Given with those major requirements of connectivity, performance, power, AI, Qualcomm becomes one of the leading providers to enable that digital transformation across these different segments of IoT. For today's session, we'll be focusing specific on one part of the enterprise IoT, which is going to be industrial inspection. So with that, how do we look at this space with respect to intelligence and connectivity? We are a firm believer of distributed intelligence. What that means is the intelligence at the edge started with on-device. So this is where mobile is one of the great examples, moving to all the other sensor-based products like cameras, audio, thermostats. We are enabling through our technologies, from hardware to software to application, on-device intelligence on those sensor-generating devices itself. At the same time, as we saw in the previous slide, there is an exponential rise in the requirements of what we want to do towards the edge. And to cater to those requirements, we are also enabling devices near and far edge to get more and more compute closer to those on-device itself. So we play in both the spaces. We play on the device, so we are enabling that intelligence on the device, and at the same time, for any of the further requirements and higher compute requirements, we are bringing in these edge products, for example, edge AI boxes, edge gateways, and we are enabling intelligence up there as well. Together, these two makes us this space of connected intelligent edge. And that's where Qualcomm is leading with all the different pillars of hardware, software, and multiple different ecosystem provider for applications in enabling the space of connected intelligent edge. So with that, I would focus specifically on what at Qualcomm starts differentiating us and cater to that space of connected intelligent edge. As we talk about, there were two major things to begin with. In the term itself, connected intelligent edge, one is connectivity. So it's in our genes from Qualcomm perspective that no matter which form of connectivity you want to think about, it's there, enabled, and constantly improving in our chipset portfolio. With that, the second thing is intelligence. So intelligence with AI, machine learning, deep learning kind of applications continuously evolving is something that we are continuously growing and evolving in our hardware as well. So you would see generation after generation, our hardware getting involved and getting more and more performance efficient and power efficient to cater to those applications. The third pillar is the computing. So computing can be called out in forms of CPU, GPU, or some of the multimedia computing with respect to camera, audio. These are all core components of our chipsets that we cater to. And just like the other two pieces we talked about, they have been continuously evolving generation after generation. And the last pillar, the last circle shown over here is security. Day by day, we are seeing more and more security protocols coming into existence. And that is where edge is becoming more and more important. At the same time, we see for applications with specific to where the humans are involved or payment kind of applications are involved, this hardware-based security with hardware root of trust is becoming very critical. And that's one of the other core pieces that is offered through the Qualcomm technologies. So these are four major pillars that we are going to talk about with respect to the enablers in this market space. Other than that, what I would like to say is the chipsets by Qualcomm, it ends up being a one-stop shop where you can think about 40, 50, 60 different specialized IP cores all in one particular chipset. So you can take that one platform and cater to different requirements. So with respect to Connected Intelligent Edge, with this one chipset, we are able to cater to different type of sensors, camera, thermal, audio, and so on. We are able to take care of the whole computing pipeline with respect to image processing, video processing with our CPU, GPU, camera, ISP pipelines and those specialized cores. We are able to take care of machine learning with our deep neural network accelerators. We are able to take care of security end-to-end from provisioning of those applications to deployment of those applications. And at the same time, we are keeping everything in a connected space with different kind of connectivity technologies. So that's, again, a one chipset solution, and that's what we are offering through the Qualcomm technologies across our chipset portfolio. Again, diving down into that connected intelligence space and how we are enabling that into some of those application spaces. So we talked about on-device, and here are some of the examples of those on-devices where we can have cameras stationed in form of a scanner or at a smart city intersection or in a warehouse manufacturing place. We have smartness enabled on these cameras. They could be doing any of the applications like a worker safety or a traffic management or barcode recognition kind of applications shown up here, and many more use cases which can be done. So that's the on-device capability. And on top of it, what we said was, as we want more and more compute coming towards the edge, we have these AI boxes coming into picture where multiple of these sensors could now be connected to this box itself, and the box can act like a metadata processing unit. So you would have multiple of these sensors. These sensors could be intelligent sensors, or it could be dumb cameras as well. That data comes into this box, and then box would do the additional compute and any kind of analytics which is needed on top of the data which is coming in. Once the data has been processed, the actions could be taken through the box itself, or for the next steps, it can go further towards a server class or to a cloud. It really depends on the application to application. So again, the left-hand side of the diagram with the on-device and then the box creates that complete connected intelligence space for us. And what we are showing towards the right is all the applications or different kind of applications that we are enabling across the portfolio. As we will see later on as well, across the portfolio in both on-device and on the edge, we have multiple different frameworks. Commonly used, called out frameworks are all supported, which is what our developer community has been using to deploy some of these applications on the edge in the connected intelligent edge space. The chipset that we are going to talk about today for this particular application deployment is the one which we recently announced at Embedded World. This is the first chipset in the market which comes with the integrated 5G and has multiple operating systems supported. So it supports Android, it supports embedded Linux, it supports Ubuntu, and it supports Windows. With all those different flavors, we provide the utmost flexibility and the scalability in a given market. What that means is if a customer is using this chipset for an application in an Android space with the same form factor, keeping the same hardware design, they can take it to a different market space requiring, for example, a Windows-based application. And that's what we are coming out with this chipset portfolio. This is the QCS and the QCM version of 6490. Some of the applications are already listed out here with respect to manufacturing, warehousing, retail kind of applications. We are going to be focusing from a deployment perspective today. The example that I will talk about would be specific on the industrial manufacturing side of use case. Quick highlights on this chipset itself. So As I mentioned before, the key technologies coming out of Qualcomm, they are all part of this one chipset, as you can see. We talked with respect to compute, so it's best-in-class compute when we are talking about the CPUs and the GPUs which are present in this chipset. Security was another big pillar, so we do get that hardware root of trust-based security embedded into this chipset itself. So you have that per device key that you can use for any kind of secured infrastructure. It has multiple operating system support that we just talked about with respect to scalability and flexibility on the market space coverage for a given customer itself. One of the best-in-class camera processing with the triple ISP for any kind of advanced processing on camera infrastructure itself, enabling that on-device kind of applications that we talked about. Video and the display qualities are again one of the top tier that we are providing in this space. And the last two pillars enabling that connected intelligent edge space is the connectivities. As I mentioned, this is the first chipset with the embedded integrated 5G itself. And at the same time, you get all the traditional connectivity with respect to be it Wi-Fi or any of the other connectivity features that you need are all integrated into this chipset. And last but not the least, which is going to be the focus for the next few slides, is the machine learning itself. So it has a dedicated core that we call hexagon tensor processor. It was our architecture where we moved into a tightly coupled design for a neural network deployment. And what that means is that we tightly coupled our scalar vector and tensor processor into one unit with a shared memory subsystem, enabling a much better performance throughput from a memory managed system perspective from this particular IP. So that's the major highlights of this chipset from a hardware perspective. At the same time, from a software, so software goes pretty much hand in hand when we talk about neural networks. We have a unified AI software stack that is used across Qualcomm portfolio, and that is exactly what we have been leveraging in the IoT side of Qualcomm as well. So as we look through this stack bottoms up, you can see that across the operating system, be it Windows or Android or any of the other operating system, we have all the above top stack which is supported. Going towards the machine learning itself, so if we look at the different AI frameworks, so most of the commonly called out frameworks, be it PyTorch or TensorFlow or Onyx, they are all supported on these chipsets across the portfolio of our chipset. We have two major runtimes which are supported. One is our homegrown Qualcomm Neural Processing SDK, and we would be using that for the application deployment that we will talk about in a bit. And we also support heavily into community with TF Lite, and TensorFlow Lite is another supported runtime for model deployment, which is heavily used out there. Last but not the least on this stack itself, for IoT specific chipsets, we have something called Qualcomm Intelligent Multimedia SDK. This is basically, again, a standard GStreamer based SDK, which is all just different set of plugins. So you can use your standard GStreamer plugins, or you can use some of the specialized GStreamer plugins that we have developed inside Qualcomm, optimized for our chipsets. And there are multiple buckets of it, from display, multimedia, machine learning, computer vision, or networking plugins. You can use these plugins to just connect together and create an end-to-end application and seamlessly deploy your application onto our chipset. So that's the unified software stack. With that software stack, we also provide a lot of tools. Some of these tools are open source tools that you can find on the GitHub. One of the commonly called out tools is a AI model efficiency toolkit, which we will call out later in our flow as well. It's used by the developers moving from a floating point world towards an embedded platform, and how to efficiently compress and quantize your model to make it embedded friendly, integer math friendly. So these are all different sets of tools and framework that we provide. And the beauty is it's basically across the chipset. So you build once for one of the chipset, and then you can move seamlessly towards the other chipset by just a simple recompile and run. And that's exactly what we have done for the application that we are going to talk about. So moving to the application that our developer over here used on the platforms that we have talked about in the earlier slides, we are focusing specifically on the industrial market for this specific presentation. And the one we used is basically defect detection, anomaly detection on a belt line. This is a very common problem that we see across in the industries, and by automating it, we are able to make that operational efficiency come into picture. So much faster detections and much efficient way of doing things, a much proficient way of doing things. So what we looked at from a developer perspective was what are the different mechanisms a developer can go and pick a model for anomaly detection. We have highlighted a taxonomy over here based on the paper listed here. There are 3 different variants that we can think about. The first one on the top, when we look at it, it's a simple mere feature extractor. So this kind of model will basically take your image and just find the major features. Once you have found the major features, then you have to go into a different model or a different application to get that anomaly, to detect the anomaly and find a score associated with it. Whereas as we go to the second one, the middle part of this taxonomy, this is where we find those feature extractors, and we also, as a second step into the model, find if those feature extractors are normal or they're anomaly. And based on if they are normal or they're anomaly, it goes into a post-processing block after that neural network deployment, and that post-processing will basically do certain customized operations to find the score associated with that anomaly. The third one, the last one in this flowchart, is basically a model that can do an end-to-end deployment. So basically you get an input image, that model automatically detects the anomaly and it finds the score for that anomaly. So there are 3 different kind of mechanisms that we can see for the model developers to take and go through the process of finding the anomaly. We pick the middle one with respect to where you would be doing a model and you would doing a post-processing to take it to an anomaly detection and a score associated with that. So once the developer was fixed on, okay, this is the path I want to take, the journey they go through is shown over here. So the first part, the dark blue that we see on the leftmost side, is for that developer. That developer decided on the architecture. They started looking at the state-of-art models, and then they have trained it for their specific data set. In this case, we were looking at some of the 10 classes across some of the industrial nuts and bolts and carpets and wood and things like that. The developer used the toolkit that I talked about earlier, the AI Model Efficiency Toolkit, to take that floating point model and run it through the compression and quantization mechanism. And once they were happy with the weights and the biases they got out of this Model Efficiency Toolkit, they go to the next step. The next step is where the deployment and the development comes into picture. And this is where we use our Qualcomm Neural Processing SDK. So this is that runtime, the homegrown runtime that we talked about in the unified software stack. In this software stack, you again go through multiple stages. You take your model that you got from the trained infrastructure, which you are happy with now, and you go through a compilation phase. Once you have a successful compilation and you have gone through all the steps, sometimes even for that compilation, there are certain operators which are not supported. Then we have the accessibility in this SDK to provide you custom ops. We call it user-defined operators, so you can add those too. For this particular experiment, we just went through, we were able to compile. And once it was compiled, we go through the quantization. So the quantization, the tool, this SDK provides you through a quantization flow. We also provide you a lot of tools that enable you to make sure that your accuracy is in check. There are, back-end flow that you can go through until you are happy with the accuracy numbers you are getting. Once you are happy with the accuracy numbers, then you can go through the conversion. And what conversion it would mean is that, okay, I'm going to take this converted model or quantized model and convert it into a model into a format that would be understood by my runtime on the device. This format for this particular SDK, we call it a DLC format. So it's a deep learning converter format. And once we have that deep learning converted format, then we can go into the runtime side itself, where we get it onto the device and use the runtime of this Qualcomm Neural Processing SDK to run it onto the device. So that's the exact flow that was used for that anomaly detection state-of-art model that we picked from the previous slide, went through this process and got it running onto the reference platform that we are talking about over here. And the next slide is basically all about from the results perspective. So if we look at the quantitative and the qualitative data points for this particular model, as I said, it goes through that whole stage of detecting the anomaly, finding the anomaly, and finding a score associated with the anomaly. The two major points that I would like to highlight over here is, first thing, floating point versus the integer math itself. So we are a true believer at Qualcomm that everything we can make it possible towards move towards embedded platform in an integer format. And these are the scores that show that even when you move towards the integer format, you are able to keep your accuracy intact. So these numbers are basically run through a standard data set, which is applicable to this particular application. And we ran through the whole data set, and these are the numbers that we get out of that. That's the first point. Then the second point that I want to highlight over here is the numbers that we are getting out of the Qualcomm Neural Processing SDK itself. So you can run that integer math on the PC, and then we can run that integer math, what we got after the quantization with the Neural Processing SDK. And as you can see, we are very close on the accuracy itself. So keeping the accuracy intact, you are able to now reduce your model from floating point to integer, and what that results into a much higher performance, much lower latency, much lower power, which is what is needed to make these applications run in the required specs on the device, on those industrial side of things. These are heavily latency critical applications which are running at sub-millisecond with high accuracy, and with all these analysis that we have done, we can perfectly say that we are able to enable these kind of applications. The charts in the down basically just show you pictorially the same thing, right? So we have used a wood slab and a carpet piece over here. You can find the anomalies, and you can see between the FP32 and the on-device int8, you basically don't see much of a difference at all, which relates to the numbers that we just talked about in the previous slide. So that's a proof point to how you can enable these applications on the edge seamlessly using our tools and sticking to the integer side of the math. Last but not the least, for the developers, please go and visit our QDN, our Qualcomm Developer Network Forum. This is a forum that we have for any of the tools and documentations that you would like to get access to. You can also get, the pointers to where to find these hardware development kits. You can get them ordered and get it running your applications onto these devices seamlessly. And at the same time, if you want to look at our ecosystem and the member space that we have, please go and visit our Qualcomm Advantage Network website. And there you can again find all the different kind of software applications and the services they are providing, different kind of hardware components from our ODM plays, and a whole ecosystem of hardware to software to services. So those are two very helpful links from both the developers to ecosystem that you can go and refer to and get going on to Qualcomm devices. So that's it for today, and thank you for listening in. Hope to see you on Qualcomm platform soon.